Thank you all for coming. If any of you were here yesterday and saw me struggle with some technical difficulties and came here today to see me struggle with the same technical difficulties, I'm sorry. We made it work. So I'm Tess. I work at Microsoft, and I've been working with LLMs for about the last year or so. And I'm sure that most of you probably have used an LLM, everyone? Yeah, I would guess like at least 99% or something. And you probably know that LLMs are very good. By the way, the subtitle of this, if you don't know why you're here, is Ragging on RAG. We're going to be talking about RAGs. If you don't know what a RAG is, you'll be acutely aware after this session. If you don't know what ragging is, you'll also be very aware after this session what that means. But we all know that LLMs are very, very good at summarizing things, like summarizing a paper, or generating a story. So in this case, generating a story about a dog that gets on with a zebra and appropriate for age 5. Because this is what language models do. This is what language models have done before they were called large language models. They were kind of predicting the next word to put together in a sentence to make the sentence look good, and generally working with text. But they're not all that good at data. So when I ask it a question like, what are my hobbies, which it won't know because I haven't publicized them on the internet, it will make up a story, both about who I am and what my hobbies, or that it doesn't know my hobbies. But it will sometimes fabricate a little bit weirdly. So in this case, it says that I'm a Microsoft MVP, which I'm not. I worked at Microsoft for the last 25 years. But this is not a huge oversight. I mean, an MVP versus an employee is not that big. But I tried to ask it again, and it came up with this. Tess Ferrandez, who is a Microsoft employee and a software developer, passed away in 2014. So this startled me a little bit, actually, when I read it. I will say the reports of my death have been greatly exaggerated. I might have stopped blogging. Maybe that was my problem. But I'm very much here, and this is not a hologram. So obviously, it can come up with both things that are not correct, and maybe also not very tonally correct. And also, if we give an example of math, and this is like a classic thing that everyone tries, give it some math problem. If you give it 1 + 1, it will obviously know, because statistically in the data that it has been trained on, that shows up a lot. But this random number that I'm putting, not so random, actually 1, 2, 3, 4, 5, 6, 7, 8, 9, but this random number, it will just answer confidently that this is the product, but actually it's not. Close, but no cigar. And this is a little bit a problem of LLMs in general, that they are not actually proper databases. It's not like we're actually extracting facts from them. We're extracting, or we're predicting the next word that could come out that may or may not be factually correct. In reality, an LLM is a probabilistic database. And if you've never seen a probabilistic database before, this is about how they work. So let's say we have a list of companies and their industries. So this is just a table of companies and industries. And now you go through and you ask, what industry does Scandinavian Airline belong to? I think most of us in here think it's an airline company, flights, travel. But this database would think it's software, because statistically, 75%, it would be software. And this is how a probabilistic database works, and this is also sort of, how LLMs work. It will take whatever is statistically reasonable as the answer. Now, probabilistic databases, they're used to clean data so that you don't put in sort of an age of 1902 or something like that, but they're not generally used for gathering, like for taking or asking data from. So what we've learned is that we can go through and we can give it some context. So I can tell the LLM in my query that I love pasta bolognese and cats. Can you give me some recipes? well, hopefully not of pasta bolognese and cats. And it gives me some recipes that kind of resonate with this. So we can ground it with some data, and we can get out some other information based on that data. So this is something that Patrick Lewis and his colleagues kind of took to and created this thing called retrieval augmented generation. How many people in here know what retrieval augmented generation, or RAG, is? Yeah? So fewer than I thought, actually. But that's good, because we're actually going to go through what retrieval augmented generation is, and also how we can optimize it, and definitely when we shouldn't use it. So the rest of the session will be how to create models that can actually reason about data, and when you shouldn't do that. So retrieval augmented generation works a little bit like this. You have a question that comes from the user, and then based on that question, you go through and you ask a database for some appropriate data. So you will have a database with data that it can use to then generate an answer from. So essentially what I did before, where I said, hi, I'm Tess, I love pasta bolognese, we're going to tell the LLM basically all the data it needs to be able to answer the question that the user has. So we search the database, we get some data out, we create a prompt from the data, and the prompt may look very different depending on where you get it from or if you fabricate it yourself, but the prompt will look something like this. Using the user-provided context to answer the user's question, you may not answer the user's query unless it's specific, unless the specific context is in the following of text. And if you don't know the answer or cannot answer, please reply with I don't know. So it doesn't just hallucinate and come up with its own answer. I'm using the word hallucinate because this is something that you'll hear a lot about LLMs, and hallucinate means basically making up a fact that didn't exist. And then we give it some data that we've gotten from the database, along with a question. And then the LLM will answer based on that. And as you saw with my pasta bolognese thing, it answered a lot more confident, like a lot better than if I would have just asked it what I wanted for lunch without context. So the way we do the searching is generally through something called embeddings. And I'm going to go through and talk about what embeddings are, because this is sort of like at the core of these RAG systems. And I would say RAG is currently probably like 75 of the applications that people do with LLMs are RAG systems. I think that will change over the next year because of the problems that we're seeing with RAG, but that is currently what we're using. And we're doing something called a semantic search using these embeddings. So embeddings are like the secret sauce of deep learning. So this is a convolutional neural network, and you don't have to worry about knowing what a convolution or a pool is or what this array is. But at the end, what happens is we will be able to determine if something is a chihuahua or a muffin, if we create a neural network, a convolutional neural network that figures this out. Convolutional neural networks are used for images. If this was a deep learning network that wasn't used for images, instead we wouldn't have convolutions, we would have like a bunch of nodes that we would teach. So this thing in the beginning, like the convolutions and the pooling, they're essentially extracting features. So they're learning filters to put on top of images. And they will find filters or features like this, lines or colors or putting together patterns. So something here, for example, we can see this looks like a little bit like a bird or a beehive or maybe a tire or something like that. And then depending on how much of this exists in the image, it then creates an array that might be, you choose the length basically, but each number in this array is between -1 and 1, and it kind of tells you how much of a tire exists in this, or how much of that beehive exists in this. So this, what we see down here, is the array, which is sort of like the embedding or the secret code or intermediate representation. This is the core of why we do deep learning. This is what we want to figure out, because this is going to help us identify if it's a chihuahua or a muffin. And the way this works is if we picture that we want to recommend a book, and I have a large number of books, and I have a daughter and a husband, and they might want a book recommendation from me. So now I say, okay, so in that case, I might sort them like this. Some are for older people, some are for younger people, and maybe my daughter wants something for the younger people, and my husband wants something for the older people. And maybe that's good, or maybe we want to kind of add another dimension to this and say, is it fiction or is it not fiction? And we can now see in this coordinate system that these books now get an array of numbers, or actually a coordinate in this two-dimensional coordinate system. So we can also see that books that are very close together, like Hunger Games, the Divergent, they end up very close in this coordinate system. And this is sort of the key to embeddings, that you can do similarity searches. Just based on where they are in the coordinate system, they will either be similar or not similar. So you can use them for recommendations or figuring out in a search. So obviously, these were just 2 dimensions, but in reality, we'll add a lot more dimensions, like math references, or if it's US-centric, or shitlit, or funny, or sci-fi, or lawyers, or would Brad Pitt play a character in a movie? It could be any sort of thing. And in fact, we don't know what it is, because the deep learning networks will come up with features that are not humanly relatable. It's features that we would never come up with ourselves, but that the machine learning model or that the deep learning model learns. And this now becomes our embedding. So we also do this not only for images and items, but also for faces, for example. So this is an embedding of this picture of my face. And this is something that was used in FaceNet in 2015. So this is quite old, like this embedding thing where what you do is like you have the FaceNet model, you extract your embedding, you put your embedding in the database, and then you take another picture of yourself, and it checks which one is it closer to. And the person that, or the hit it finds that it's this image embedding is closest to, that's the person it thinks it is, if it's close enough, because you might also have determined that they should be within a limit close to each other. So here we can see, for example, I'm the cyan person up here, and you can see that all of my pictures neatly fit together in this 2-dimensional projection of 128-dimensional embedding. And we can also see that, for example, my features maybe are quite similar to Tom Cruise and Sandra Bullock, but not so much to Bill Clinton or Serena Williams. But this is something that's super useful for similarity searches. So we can do this with images, faces, but we can also do this with words. And the way it works with words is like this. And by the way, everyone who talks about word embeddings is going to talk about man and woman and king and queen, because this comes from a very old paper on embeddings, I think from 2013 or 2011. So what we can see from this image, if we extracted the embeddings for these words, we can also see something interesting happening, where if we look at the direction between man and woman, and uncle and aunt, and king and queen, the directions between these arrows are very, very similar. And this direction, or this vector between them, kind of explains female. You know, the longer you are along this vector, the more female the sentiment of the word probably is. It's not going to be exact. These dots are a little bit too exact because, you know, queen may or may not be female, and they may or may not be royal. But as far as like the statistical meaning of them, they're probably female. And same thing if we go for man and king, woman and queen, we can also see that we can extract the sentiment royal from it. So all of this is what the large language model learns, or like the embedding models learn. They learn to extract the semantic meaning of a word or of a piece of text. So we can basically enter any piece of text and it will extract things. It will extract all these features and tell you how much of each they are. So once we know what these embeddings are, the idea behind how the search happens is this. We bring in a number of documents. So this is like our core data that we want to feed to the LLM. And then we chunk them up, because LLMs don't necessarily have, you can't necessarily put the whole document in the prompt for the LLM, specifically if you have very long documents. So you might just want to put some very small chunks, very precise chunks of data that you pull out of the database. And then we take the embedding of this chunk, so the semantic meaning of this, and we store it in a vector database. So this is what we do as preparation. And then on the other end, we go through the whole thing where we take the question and we compare the question to the potential chunks in here. So let's see how this looks in an example. So here we have, and I'm sorry if you're not a Python person, but this is going to be Python. Hopefully you can still read it somewhat. So I'm using Python, and I'm using a framework called LangChain. There are multiple frameworks for building LLM applications and RAG systems, like semantic kernel or llama index, or a number of these. But LangChain is a very common one that's used for Python. So we read in the docs, and I'm actually also extracting some metadata. So the data that I'm looking at here is actually this. We have an engineering fundamentals repository where we write things about agile, or about things like automated testing. Let's see. Well, anyways, about automated testing and CI/CD and all sorts of things. And this is what I'm reading in. Here I have all of these files in markdown format. So if I go into something like machine learning, I have like ML data exploration and things. So I'm reading this, and I'm also checking the structure, and then I'm going through and I'm doing chunking. So this was the second part. So for this specific example, I'm using something called a markdown text splitter, and I'll go through what chunking, how that works in a second in a PowerPoint. But this basically then divides the documents up into parts, and then we go through and we embed the docs. So for embedding, we use an embedding model. In this case, I'm using an OpenAI embedding model, but there are many, many different embedding models used for different purposes. So I'm using this, and if we look at an embedding, for example, of the sentence, hello world, it will then spit out an embedding, like an array that's 1,536 numbers long, and looks something like this. So we saw it similarly to when I was showing the embedding of my face. And then I'm adding all this to a vector database. And there are plenty of vector databases. Right now I'm using Azure AI Search, but you can use in-memory vector databases and all sorts of things. So they all work pretty much the same. They have a few different features depending on which. So this is what we do to sort of get the data into the system. And then if we look at something like I ask a query of this, like what are the agile ceremonies, it will then spit out the most, like the chunks that are most similar to the query, what are the agile ceremonies. In fact, if we go in and look here at this is the AI search database, and I ask it something like, what tests should I run on an ML model? It will then spit back, hopefully, a number of documents. Let's see if, so that contains something about model load predict. Let's see, I wanted to minimize this, but let's see if we can scroll down. I think because it's so big, I can't. Well, anyways, trust me that this document is probably from the ML testing document, and it will have sort of like 10 or, depending on how many you want from your query, it will have 10 or 20 chunks that it can pull out from AI search. And then if we go back, so now we have the data in there. And then to query the data, we basically set up the same things. So we have the AI search and the similarity. And then we build something called here a conversation retrieval chain. This is something that exists in LangChain. You have similar things in the other framework models. And we put in the Azure AI search as a retriever. So the only thing we then, so this is essentially how you set up like the whole RAG chain. And it will automatically create the prompts and everything for you. And then if I search for what test should we run on machine learning code, I get out an answer that looks like this, where now the LLM has synthesized all the information from the chunks that I used and given them back to me in sort of like a natural language format. I also like to do something a little bit, and this is something I do suggest that you use if you're working in Python with these LLM things. This is a tool called ChainBot. So ChainBot is a library in Python that allows you basically to create a user interface for your LLM experiments. And I've just added the exact same code that we just saw, but to Chainlit, just to show you really quick how Chainlit works. Basically, you just implement an on message. So when you get a message from the user, you just take it and send it off to the chain. And you get this whole user interface for free. So now if I say, what tests should we run on ML models? It now goes through and does the search and also synthesizing the results. I'm using the GPT-3.5 model for the results for this. And we see it came back with approximately the same thing that we saw in the notebook. And I'm also displaying like the source documents here, so we can see where it got all its information. But I find this is quite useful, is to have real users test the system. And you can actually use Chainlit in production if you want to as well. So that was our little RAG demo. And these were the tools. So now when we have the RAG demo, it's quite tempting to go from this seemingly really nice question and answer machine to artificial general intelligence. Like it's almost, yeah, there's no step between there at all. Or at least production, because, I mean, what else is there that we need to do? But it turns out that unlike sort of software projects where we create a POC and we know it can be super, super hard to figure out like how long it will take us from this POC to an actual production system. We know that there's a whole lot we need to do, but we at least have a general idea that if we can do it in a POC, we can probably also do it in real life. And we know that, yeah, setting up the real infra, setting up all the tests and everything, it will take some time, but we have a ballpark of how long time this will take. In this case, we have nothing like that. We don't even know from this small POC, which took us 5 minutes, to actually figuring out if this is even doable in production. And this is one of the problems that you kind of always have with machine learning and also with LLMs. Because the problem is that when we look at the real data, or when we look at the real sort of situation, it might turn out that the data that we had for this small POC was just, nice data. But if you went to Malte and Matilda's talk about Planprat yesterday, you saw that going through and wading through PDFs with tables, where all the tables look different in all the different documents, or they might have images or handwritten text and all that sort of stuff. It's a nightmare to even ingest the data or figuring out if the data you have will actually answer the questions that you want answered. Because if you're not giving it the proper data, it will never be able to answer the questions. And then chunking, which we'll look at in a bit, also matters a lot. How big the chunks are, and how you chunk them. And the embeddings matter a lot, and they depend a lot on both the size of the chunks and for example, if you don't have English language or things like if you have text that's maybe not general, maybe it's medical text or something like that, that's a problem. And then we need to think about, because we're now storing this data in a database, in a vector database, and this data might have come from a system that was safe and secure and had privacy, because we all are really good at both security and privacy, right? And now suddenly we're copying all the data into a new data store, and we're forgetting about all that. So maybe Anne can now get to Pete's data, or maybe people can get to data that they absolutely shouldn't be allowed to see. And not only that, but what if the data is continuously updated? How do you update this vector store with that sort of thing? So there are a lot of considerations around the data that you don't have to worry about in the demo that are very, very worrisome in real life. And then you have the question, because when you're creating this system, you're probably going to ask it some really neat and nice questions based on what you're thinking, but then a user comes in and they ask something completely different. So instead of asking some very precise questions about what tests should I run on machine learning models, they say, can you summarize all the problems I've had from between 2001 and 2018? And suddenly, there is no way that your system is built for that. It's no way your system is built for actually accessing all the chunks that you needed to answer that question. And also, you might have people that do adversarial queries. So they might go in and try to jailbreak the system in different ways. And then the retrieval, like this is a search problem that has existed since semantic search kind of started in 2013. It's not super trivial to do retrieval from a semantic database. It's not like it's going to give you 100% of all the documents that are relevant for this problem. And then we have the prompting. And the prompting, I'm sure you've heard the name prompt engineering. I think maybe not so much engineering, but prompt hacking, maybe. But it doesn't matter. Like even a word or two in your prompt creates completely different answers. And then we have the generation, which we already see how that can end up, telling people that they should have done more stuff since 2014. So all of this might seem like a ragtime nightmare. But there are things that we can do about it. So hopefully I'll introduce some good ways that you can optimize all of these things. But before we start optimizing anything, we need to talk about evaluation, because when you do experiments, a lot of people will do experiments and then evaluate them manually. And that is probably the worst thing that you can ever do, because there is no good way then to tell if chunking it this way or parsing it this way will actually make a difference for your whole system. So a long, long time ago, back in the day when we were just doing regular machine learning, like last year or something, we had these machine learning models that would do classification, for example. It would figure out if it was a cat or a dog. And we knew that if we got these answers, so it didn't realize that this was a rag doll, it thought it was a dog, we had 90% accuracy. And what we would worry about was if the test set was different enough from the training set, so we didn't leak data from the training set and the test set. So I'm not saying that it was always this easy to figure out what the accuracy was, but generally we had something called accuracy that we could deal with. But now we have something completely different, because now we're generating text. So if we're generating text about this image and the ground truth, assuming that we actually have ground truth, because that's a problem too. Like we have to evaluate something, we actually have to have someone write down a number of questions and a number of answers that they would like to have. So in this case, if I say this is a pic of a super cute kitten catching some C's, and that's the correct answer, but how good is this answer? An image of a sleeping feline raising her paws. Obviously, it's factually correct, assuming that it's assuming it's a her, but it might not be tonally correct, and you can see that the words are very different. So it might also be semantically correct, but we have no real way of telling, like, is this a correct thing? If this would have to fit in a book for a 5-year-old, this might not be the perfect answer here. It might be very incorrect. And oftentimes it's not even factually correct. So it's very hard to say what the accuracy is here. We have some attempts to do this. So, for example, prompt flow in Azure has a number of measurements that it can help you take. And same thing with like frameworks like Ragas that will help you evaluate different things. So on the retrieval side, it might evaluate context precision and context recall. So what this does is it basically say, given the question, context precision is the chunks that I got back, are they actually, like, do they fit the question? And context recall says, did I get all the chunks that were necessary to answer the question? So that's on the retrieval side. And then we have groundness or faithfulness on the generation side, which means, did the LLM use the context to generate the answer, or did it just come up with answers by itself? So out of the facts that it stated, how many of those were actually grounded in the context it was given? And finally, there is things like answer relevancy, which is, did the question or did the answer actually fit the question, and so on. So all of these, we can now see that we have 4 different measurements, and we all know that if we have 4 measurements and we try to tweak something, and that tweak fixes this, but doesn't fix this, then what did we do? How good was that fix? So it becomes harder and harder the more things you have. But the other problem with this also is that this is typically based on asking an LLM to give an answer, basically to tell it, was it factually correct, or was the context relevant? So we literally have an LLM watching an LLM. And if the LLM that we used to generate the answer was GPT-4, and the LLM that we're using to watching GPT-4 is also GPT-4, then do you think it will tell that it's correct or incorrect? So these are some problems that we have to wade through. It will be a little bit better if you have GPT-4, for example, watching GPT-3.5, because then you have a better LLM that can sort of tell you how factually correct the lower one was. But so these are all problems, but this is what we have. So at least we have something that we can use to test these things. So now that we have something to test, let's talk about like some of the optimizations we can make. So the first one is around data and data ingestion. And I think that in all machine learning projects, and the same thing with these LLM and RAG problems, this is the most important part of the problem, which is actually making sure you have the right data and making sure the data is ingestible, so that it's not out of date, that it's actually is complete, will answer the questions you need, and also like that when you extract it. So if you extract a table, deciding like how that will look, and you might have other problems in your PDFs, for example, with images or all sorts of things. So one thing we can use is document intelligence. So document intelligence is one of the tools that you can use to do a little bit better parsing than normal if you have PDFs. There is also Llama Parse, which is something that came out now from Llama Index. But there are definitely better parsers that you can often use, especially if you're working with PDFs. So I'm just bringing this up because this, before Llama Parser, actually, I think llama parse and document intelligence are kind of like on par, but this used to be the state of the art for extracting things from PDFs. It's not something that you use locally on your machine. It's actually an API that you have to go through with models in the background. And if we have multimodal data, multimodal meaning that we have images or we have tables or we have things that are not necessarily plain text, a couple of things that we can do are, for example, if you have an image in your PDF, you can either ignore it and say that I don't care about the images, but then you'll lose some data. Or you can do things like try to get a caption for the data and you store that with your text chunks instead. Or try to extract and summarize your tables or extract them as JSON or something. Or use a multimodal LLMs. And now we have like ChatGPT 4v and 4o that know multiple modalities, so it knows images, etc. Now we get to the chunking. So the chunking basically means how we split up our data into smaller parts. And we want to make sure that we pick a chunking method that's fitting our data. So if you have a long novel, then the context that you need might be sort of like a whole chapter or something like that. Whereas if you have a Q&A document, you might want to chunk them up in just a question and answer. And that might be the correct chunking part. And you also have to think about, different embedding models have different sizes that they work well with and not, and different LLMs have different context windows, like how many chunks you can actually put in or how much text you can actually put in. And the other thing you want to do is also try to balance, because we're using, in the general case, which we'll see we can change, we're using the question, creating the embedding of that, and comparing that to the chunk. We want to make sure that they're approximately the same size. So if you try to embed something that's a page long, that contains a lot of different topics, then the embedding for that is not going to be very precise. It's going to be super general because it's going to have all these semantic meanings. And it's going to be very hard to kind of compare that to a very crisp question. So chunking works like this. So this is the most naive type of chunking. And if you want to try out chunking, there is this site called ChunkWiz where you can test out how chunking would work for your documents. But this one basically says, chunk it up into 400 characters at a time. I don't care where that 400 characters take me. So you can see here between the blue and the yellow on top, it is stopped in the middle of a word. Obviously, if we send in that chunk to an LLM, it will be missing some context at the end of that sentence. It's like if you would just tell your friend half a sentence and then ask it to give you an answer based on that question, on that sentence. So a little bit more refined way of doing this is by doing a recursive sentence splitter or a recursive character splitter, and it will at least give you paragraphs, or it might look for sentences or things like that. So this is the typical thing that you'll see in most demos. It will use this recursive character text splitter. But I think we should go a little bit further and do something like this, which is a recursive text splitter, but with, in this case, since I'm using Markdown, it will know about Markdown, and I will say, pick out chunks that are like second-level headings. Those are the chunks that I want. And this recursive text splitter also has modes for HTML or for Python or for a lot of different things. So depending on the context, there is often like a splitter that will understand your type of content and be able to split a little bit more intelligently based on that. Or you can create your own splitting yourself, but basically try to be as content aware as possible. And then if we're talking about the embedding and indexing, I've already talked about how we want the chunks to be super small because the chunks are sort of like what we're going to be comparing to the question. So we want to have a crisp topic. We want to have a crisp embedding that basically is very specific to that chunk. But when we give the context might need to be a lot bigger for the LLM. So as an example, if we have this document, which is the plot of Oppenheimer, and we have a question that is, what was Oppenheimer's relationship with Einstein? It might have picked out this chunk, but this chunk might not tell the whole story. This was because this chunk contained Einstein and something like that. So we pick this out of the database, but we send the LLM this. So we send the LLM the chunks before or after. So this is a technique called small to big. And it's quite an easy technique that I think is well worth experimenting with. There is also another version of this where we do the same thing, but where you're sending back the whole document altogether. Or we might have a summary of the page that we use for indexing, and then send back the whole page. And how much we send back depends on what LLM we're using, like how big its context window is, and how many chunks we might want to send back. So this particular one is called parent-child chunks retrieval. We also have a number of other techniques, and I will say that a lot of these techniques may or may not yield results in your specific case, but they are quite interesting to try out. So the next one is called HIDE. This is a paper that came out that talks about hypothetical document embeddings. So when we have the question, instead of trying to embed the question, what we do is we ask an LLM, can you give me a paragraph based on this question? And then we use an embedding of the paragraph instead. And the idea behind this is because you might have a question that goes, can you give me a passage from War and Peace? And then you want this, which actually has nothing to do with War and Peace. Like, it doesn't contain the text of War and Peace in any ways, but it might be very similar to a hypothetical chunk that the LLM spits out. But now we're kind of in the realm where we're asking an LLM to guess what an answer might be, and then try to retrieve something from a database on what that answer might be. The alternative, or the reverse of this, is that when we embed all the chunks, instead of embedding the chunks, we say, can you please give me a question that someone might ask about this chunk? So the LLM would then spit back a question, and instead of giving the embedding of the chunk in the index database, we give the embedding of the question that the LLM came up with. So now we're comparing questions and questions, because it's quite important when you look at embeddings that you're comparing apples and apples and oranges and oranges. So this is one technique. The other thing with embeddings is this. If we have a legal text, like in this case we have words like hereinafter, which, yeah, I've never used that word in real life actually, but or commencement date. Or if we have a medical text, it might be something like a wet lab or a solution. And solution in medical cases or in chemical cases is a lot different than a solution in general text. So now if we're using an embedding model that's built for general text, that might not find the sentiment of solution in this case. So we might want to just train and fine-tune. So fine-tuning means that you take a model that already exists, like an embedding model, and then you train it a little bit more with just a few more examples so that it learns what a solution means in your type of text. So you train it a little bit on your own data. Then we have the indexing and retrieval. So now we're going to get into some other techniques that we can use for that. So this one is one that I will say, if you do nothing else, and if you have the opportunity, this is one that you absolutely do want to try. Metadata filtering. So we can picture a number of queries that we might be able to ask on a number of, sort of like if we have information or the plots of some movies. So we might want to say, I want to watch a movie rated higher than 8.5, or something that's directed by Greta Gerwig, or something like that, where in traditional means we would do filtering on this, but they're not giving us a filter. They're giving us sort of like the question in plain text with kind of hidden filtering and questions. Like, for example, has Greta Gerwig directed any movies about women? That's actually movies about women, director equals Greta Gerwig. That's how we probably would want the query to show up. So the way we do this is we can now bring out the same chunks, and if we have the metadata around them, and this might be, in this case, we have very good metadata, like what year or rating or genre or things like that. But you might have at least some metadata about where the PDF came from, what machine it was talking about, if it was talking about like how a machine works or something like that. So you can kind of like add metadata to your content, and then you can tell also the vector database, sorry, not the vector database. Like you can specify the metadata fields. This is for the retriever, to say this is the description of the metadata fields. So when someone comes in and talks about genre, then this is what they might filter on. And these are the possible answers that you might have. And then you go through and you retrieve the content, and you get out sort of things filtered. So if we look at how this looks in real life, you'll see here, I've done the same thing here. And the prompt that it actually asked the LLM in order to do the filtering was, your goal is to structure the user's query to match the request schema below with a query and a filter, and it tells it how it should generate a filter. So basically, we're asking the LLM to create a filter for us into the index database. And this works extremely well, actually, assuming that we have the metadata for the data we have. So another thing we can do, and when you're doing some of these things, you have to be a little bit aware that some of these things take an extra call to an LLM in order to be able to execute. And you will have to like consider if it's worth the cost and the time it takes to make that extra call. So this is query expansion. You have a question, and you ask a machine learning model or an LLM to say, give me 5 questions based on this question. And then I take all of these 5 questions, and I search the database. And then I pull together sort of like, I look at the unique chunks that I get back and re-rank them. So re-ranking you often do with a re-ranking model. And then you ask the LLM to synthesize the answer based on that. And the idea behind this is that the user might have asked like a very vague question, like maybe what are the approaches to task decomposition? But if we can expand this to these questions instead, it might have a better chance to actually retrieve the content from the vector database. Or it might even sort of create like sub-questions. So it might create, from one of these, it might create a number of sub-questions that together bring up all the data that we need to answer the question. And then we have hybrid search. Hybrid search basically means that you both do semantic search, but you do some more traditional search or n-gram search, where n-gram is basically more traditional NLP searching. So you can say, I want 25% of my results to come from this type of search and 75% from this. And you can mix and match however you want, and then take the chunks and reduce and re-rank and do this. So this is also something to try out, and most vector databases have this kind of capability. And then when it comes to re-ranking, you might think that if you've gotten something from a vector database, it should already be ranked nicely, like we get the best things first and the worst, like in diminishing order. But it's not necessarily always true. We might use a re-ranker that's better at actually the ranking portion. And we also might have a problem like is described in this paper that's called a lost in the middle problem. So it turns out that a lot of LLMs know things that are at the beginning and at the end of the prompt, but they don't know, like they kind of forget about things that are in the middle of the prompt. So you might want to re-rank and put the important stuff first and last. Like Claude 2 kind of like often listens more to the things that are close to the questions. So it depends also what LLM you're using, how it's using the context, and how it's doing this. And then when it comes to the generation, there are a couple of things that we can do. We can use something called agents. So I'll show here. We'll call this agent Mr. Anderson. So we saw from before that it wasn't very good at math. And it's also not good at actually searching for things or finding data that's very recent. So in this case, what I want to do is I want to say, how many more people live in Stockholm versus Oslo? So what this is going to do is it's going to go first out and do a web search, and then it's going to use a calculator to put things together. And before I show the answers, I'm just going to show you how this agent looks. So the only thing I've done here is I've created a set of tools. So one tool is a search, and one tool is a calculator. In this case, I've used the Bing search. The reason I used that was because I had the API key. And then I'm using OpenAI to kind of synthesize the answer once it's gotten the results of both of these. And then you can see this agent, what it does is it kind of uses the LLM to figure out how it should solve the problem based on what the question is. And one way it's doing this, then it took 5 steps. So first, it had a thought that it should use the search tool for the current population in Stockholm and Oslo. And it goes through and does the search, and then it used the results and it put them together, and it used the calculator tool, which the calculator tool is basically just a function like that can calculate. So this is not a guessing anymore. Like the calculator tool is an actual calculator. And it returns the answer. And all of this took and then it comes together and creates an answer for us that we can use. And all of this took one step and all of that. That's a part of Chainlit, this user interface, that makes it also quite nice to work with these agents and things. Just because you can kind of like run a lot of queries and you can follow the whole train of thought and everything. So sometimes we can use these agents to figure out first, if you have very similar documents, let's say you have documents that talk about different machines and how you should operate them, then you might have document agents that know first which document you should run RAG on, and then use that instead of like having all the chunks together in one RAG system. And then finally, with all of these things, there is still something very scary going on. This is an LLM leaderboard. There is like a lot of benchmarking when it comes to LLMs. This is just one. I just picked one, the first one I could come up with when I searched for LLM benchmarking. But they will all show about the same things, that on data sets that it's trained on, it will find out the general accuracy of how well it answers something is around 65 to 85%, or 60 to 85%. And they're getting a little bit better. I think GPT-4o is a little bit over 85% in general. So we're kind of getting there. But right now, it sits at about 85%. So we know that generation then is definitely not a 100% thing, even given all the context in the correct order. And then we have the retrieval, which itself might have an accuracy of maybe 60 to 85%. Yes, ballparking here, but these are quite reasonable numbers for retrieval, and augmentation. And if we look at this, now we have two probabilistic systems that we compound. So we have 0.85 times 0.85, 0.72. So that means that on a good day, it will answer correctly 3 out of 4 questions. And that fourth question, it will also be very confidently incorrect, you know. So unlike something like where we return a bunch of search results and we give the user 10 search results, the user is quite used to that it will have to sift through the search results, and if it's a good search, then hopefully one of the 3 first things will be correct. But it will itself, like the user will themselves go through and say, not relevant to me, yeah, my question was probably not good enough to give me, like, but out of the maybe first 3 or first 5, it will find the answer. In this case, we're assuming that all of our 5 first guesses are correct, and we're using that as the facts for the LLM to generate the answer with. So what happens here is that we might create a system, and especially if this is a sensitive system, like we were experimenting with just a really rough experiment where we had a knowledge base, an HR knowledge base, and we wanted to create sort of like an FAQ on top of it. And it would confidently tell us that if your cat passed away, you had 3 days of vacation, or not vacation, but you could take 3 days of leave because of this. And when you're getting told this in natural language, that is fact. I mean, if you're asking an HR bot to give you an answer, you're going to trust what it says, especially if it's, well, you might trust it, but you're probably going to point to it and say, it told me this. I should get these 3 days. So if you have a sensitive use case where someone, like where what you're saying is legally binding, or what you're saying is actually going to affect someone on how they're going to process something. Like let's say you have something that returns how you should operate a machine, and it forgets to tell you 1 or 2 steps, and those steps are quite crucial to how you should operate it. Maybe turn the machine off before you clean it or something like that. That might cause some real actual problems in real life. So be very careful if you're using this sort of in a real sensitive use case. So that kind of post this paper. It says RAG does not work for enterprises. And actually one of my colleagues asked, Tess, did you co-author this? Because I've kind of been a little bit on the rant or rag for this. Yeah, no, she didn't. Yes. So what we can do here instead is basically take off the augmented generation in these sensitive. And by sensitive, I mean sensitive in the widest sense of the word. Yes, do search, maybe add data in templates, or do highlighting of the search results when they come out instead of augmenting and actually generating an answer, in natural language. And finally, the last sort of thing that we need to take care of is guardrailing. So there is a lot of things that might happen where the user might have an adversarial question, or your LLM might answer something that it shouldn't answer, maybe the tone is wrong and things like that. So from this very naive RAG system, we should add a lot of guardrails, like check if it contains PII, so we don't send PII to a language model that we don't want to send PII to, or if it's asking something that's completely off topic, we need to understand if we need to give answers that are appropriate, or if they do a jailbreak attempt, we need to stop that. And on the other side, also fix all the things that can come out from the generation, like hallucinations or bad tone, or if it's supposed to return a piece of code, testing that the code will actually work, things like that. That it doesn't return secrets, etc. So all of this together are things that we can do to make these better. But I want to just finish off with saying, rack carefully out there, friends, because this is, while it looks shiny when you first try it out, there's a lot of work that needs to be done before you're finished. So thank you so much for listening, and I'll be here for a while for questions.